Hello there, ROS developers, and welcome to a new open class. We are today in open class number 195. And today we have also a very interesting class where we are going to be combining a little bit of work in a simulation, and then later also I'm going to also connect to a real robot. We are going to be working with the LIMO Pro robot, super cool robot, especially for education purposes. I'm going to be explaining more of the robot in a moment. And the topic for today's class is how to integrate a custom controller into your navigation to stack. So yeah, I hope that you are going to enjoy it a lot. I think it's a quite interesting topic. So yeah, without further ado, let's get started. So yeah, let me already switch here to my computer screen so that I can have the chat and everything here ready. Give me 1 second. There we go. Okay. So let me open here the class and have the chat available here. Hello. Gilbert says sound and video is good. Project is loading. Let's go. I like your attitude, Gilbert. That's the good attitude. Bartos says hello from Poland. Hello there. All right. So yeah, let's get started. Then before getting started with the class, the very first thing that we need to do, that you need to do, is to get a copy of today's class project. What is a project? If you have been attending to previous live classes, you already know. But in case that you are new, which might be the case, we usually have always new people coming to the classes. So a project is a cloud-based ROS project, okay? And I am creating these projects for every class and sharing them with all of you so that basically you can reproduce everything that I'm going to be doing during today's class. Yeah? So these open classes are interactive classes where I want all of you to be working with me, to be testing everything and working with robots also. So not just listening and watching to what I am doing, okay? Then how can you get the project for today's class? Super easy. All you have to do is to click here in the button that you have right above the chat, which says fork and open the class project. Okay? I'm going to click here myself. Let me click here. So all of you, please do the same. Click on the button if you haven't already. And then a couple of things are going to happen. So I closed this. Let me open it again. So first of all, you are going to be redirected to the main project page, which is the one I am right now here. Yeah. And here in the right side, you are going to have the streaming area with the video, the chat, and everything. So I'm going to remove this from this screen just so that I can have some more space here for the project and for showing everything properly. And I will put here the chat so that I can see your messages. There we go. Okay, and then you have to wait some seconds, and after a few seconds, the project environment is going to finish loading. Okay? Then meanwhile the environment is loading, let me also explain to you that by clicking on this button in order to get today's project, also you are creating a copy of this project in your account. Yeah, a permanent copy. So if you come here to the left menu and you go to the option My Projects, which you can find here in the left menu, My Projects. If you go inside here you are going to find all your projects, and the last one should be the one that you have just copied. Yeah? And this is interesting. Why? Because you are going to have access. So this project is in your account, is yours basically forever. Yeah? So not only for today's class, but you are going to have access to this project in case that you want to get back to it next week, next month, or whenever you want. All right? Okay, then let's go back to the project. And here you can see my project environment has loaded. Let me close all these things. Yeah, because in your case, probably what you are going to see is something like this. Yeah, once the ROSject environment finishes loading, you are going to see here, or you should see, the notebook for today's class here automatically opened. Yeah, custom controller integration with Nav2. Yeah, so this is the first step. Then give me some feedback there in the chat. Has everybody been able to properly open the ROSject? And are you here in the same page as I am with the notebook opened? Yes, no, any issue so far? Yes, yes, fine. Yes, okay. So it looks like everybody is set up and ready to get started with the class. Awesome. Okay, then the very first thing that we are going to do now is to launch a simulation, the simulation that we are going to be using for doing today's demonstrations and to properly learn through practice how to integrate a custom controller with a navigation to system, okay? So we are going to start by launching the simulation, and the simulation for today's class is going to be based on the LIMO robot from Agile X. Okay, we are going to start by launching the simulation, which is a super cool simulation, by the way, and then later I'm going to explain a bit more about this super cool robot. But what to do in order to launch the simulation? Very easy. All you have to do is to follow the steps that are described here in the notebook in the Let's Launch the Simulation section. And basically here you have a couple of commands, all right? So we basically need to execute these commands. So how to execute these commands? Well, we need to execute them in a terminal, in a shell, right? So the very first thing that we need to do is to open a new terminal, right? So that we can start working. Then, very easy. In order to open a new terminal from the ROSject environment, all you have to do is come here to the bottom menu. You are going to see here many options. And the very first one that you can see here, it says Web Shell. If you click on this button, this is going to open a brand new terminal. This is a regular Linux terminal where you can type commands, etc. All right? Then once you have the terminal, you can just copy and paste directly here from the Jupyter Notebook. You can copy the commands and paste them here directly to the terminal. Okay, this is the easiest way so that you go faster. And then if you execute these commands, you are going to start seeing some messages here in the terminal. And after a few seconds, you should see the simulation window pop up here. Okay? This might take some seconds, and in case that it doesn't pop up automatically, don't worry, okay? It happens sometimes. All you have to do is to manually open the gazebo window, okay? So how to do that? Again, you have to go to the bottom menu here where you have all the different options, and then the fourth one here, it says Open Gazebo, GZ Web, okay? So it's this cube that you can find here. Then if you click here, this is going to open the gazebo window, and here, after a few moments, you are going to see the simulation loading. There we go, okay? So here I have, in my case, the simulation. You can see here the LIMO robot, tiny LIMO robot, yeah? And then if you zoom out, you are going to see that we are in an office environment. Very cool. So this is basically the simulation, the environment that we are going to use in order to demonstrate today's class, okay? We are going to start working on this simulation, on this simulated version of the LIMO robot, and later we are going to switch, I'm going to switch in this case, to a real LIMO robot. I'm going to be connecting to a real LIMO robot and see if everything that we do in the simulation, we can also replicate it in a real robot, yeah? So far, so good. Has everybody been able to load properly the simulation? you should see something like this, okay? This very nice office environment with the LIMO robot here spawned. Let me go back to the chat here. Gazebo manually started, simulation loaded. Any issues? Is everybody been able to load the simulation? Yeah? So in case it doesn't pop up, don't worry, just you can click manually here on the gazebo icon and then it's going to open, okay? Loaded, all okay. Okay, excellent. Excellent, so it seems that we are good to continue. Then, before continuing with the class, I want to introduce you to this LIMO robot, all right? We have already been using this robot in previous classes, but maybe some of you don't know about this robot. And this is a super cool robot, and it's especially cool for education purposes, okay? In specific, the LIMO Pro version, it includes things, very basic sensors in robotics, such as LiDAR, IMU, RGB depth camera for producing a point cloud information. It also provides an NVIDIA Jetson Nano, a very cool display in order to visualize RVs or whatever you want. And it's a very interesting robot also because, as you can see here from the image, you can switch between different steering modes. You have the typical differential drive steering mode, but you can also use and switch it to work with an omnidirectional steering, but also even Ackermann steering. Yeah, so it provides many options. You can teach kinematics, for instance, using the different steering modes. You can teach things such as navigation, which is where we are going to be focusing today. You can also teach things such as perception, as it is provided with an RGB depth camera. Topics such as AI, and take advantage of the NVIDIA Jetson Nano, machine learning, many different topics can be taught using this LIMO Pro robot, and also for personal projects, research, etc. Super cool robot, which has an official price of $3,420. But for the attendance to the open class, we are providing a coupon code so that you can get almost $500 discount. Yeah. So by using this coupon code, you can get a LIMO Pro robot for only $2,999. Okay. Let me drink some water. This coupon is valid until September 3. Okay, so don't hesitate too much, because otherwise you are going to lose this opportunity. And you have the link here in order to get it using the code. Yeah, so this is going to take you to the buy page, and here you can insert the discount coupon. Yeah, here you can see the official price, but after applying the coupon, you are going to get the discount in order to get it for $2,999. Okay. As I was saying, super interesting robot, super cool robot, which provides many features. And also, in addition, we have a set of courses in the construct that you are going to find here at the bottom of the page in related courses, which basically teach you different ROS2 subjects using this LIMO robot. Yeah. For instance, you have this course of Mastering ROS2 with LIMO Robot, where you are going to learn about topics, about navigation, obstacle avoidance, 3D mapping with AirTap map, many different features. We also have another course of using the LIMO with manipulation. But yeah, so we have many material in our platform in order to teach ROS2 topics using the LIMO robot. All right, so yeah, very interesting option. You have all the information here, and yeah, in case you are interested, go ahead, because I'm sure you are going to love it. Super, super nice robot. Okay, then with all the introductions being made, I think it's time to get started with the class itself, with the topic of the class. So let me very quickly go one last time here to the chat and see if there are any comments. Nothing. I can see Sonia here sharing the link. Okay, then let's get started. What is a Nav2 controller? Does everybody know what is a controller in the context of navigation? Do you know what is known as a navigation 2 controller? Everybody? Yes, no? Let me know here in the chat. Mario says no. I'm not going to go for that name, I'm sorry, but he also says no. Also Martin says no. Okay. Okay, don't worry, because this is what we are going to explain right now, okay? So what is a Nav2 controller? Okay, then a navigation 2 controller is a key component of the navigation 2 stack in ROS 2, which is responsible for the low-level control of a robot during autonomous navigation. Sorry. Yeah, so everybody knows what autonomous navigation is, yeah? It is the skill of a robot of being able to move autonomously from a point A to a point B while avoiding obstacles. Yeah, in general terms, this is what we know as autonomous navigation. But autonomous navigation, it has many different parts. Yeah, many different components. One of these components, which is a low-level component, is the controller, which is in charge of controlling on a low level the robot in order to make sure that it achieves, it reaches properly its goal. All right? Then what are the key responsibilities of a controller, of a navigation 2 controller? First of all, path following. Yeah? So the primary job of the controller is to follow a given path that has been previously planned by the global planner. Yeah? So we first compute a global plan, and then the navigation 2 controller is in charge of making sure that the robot properly follows this plan on a lower level. Okay? I'm going to introduce this a little bit now, and in a moment we are going to see a practical demonstration. Okay? Then also local decision making. Yeah? So the controller needs to make real-time decisions to adjust the robot's movement. Yeah? For instance, what happens if there is a person which suddenly tries to cross in the path of the robot? Yeah? So the robot needs to be able to make local decision. It needs to be able to make local decisions, real-time decisions, in order to avoid any possible dynamic obstacles that appear, that are not expected. Yeah? Yeah, it follows the path while avoiding dynamic obstacles. And how it does this dynamic obstacle avoidance? Well, basically using the laser. Okay? So here I'm explaining some navigation 2 concepts, okay? Maybe I'm going too fast and you might be a bit lost, but unfortunately we don't have time to explain everything, yeah? But all these things are navigation 2 general concepts, okay? Also, another key responsibility of the navigation 2 controller is the velocity commands, yeah? So the controller is in charge of sending the proper velocities to the wheels of the robot in order to make sure that the robot follows the path. Okay? Yeah? Obstacle avoidance. This is related to point 2, which is local decision making. So the controller can take into account sensor data, for instance, the LiDAR, the laser, in order to avoid obstacles that might appear on the planet path. Yeah, dynamic obstacles. And finally, this controller can be customized through parameters and can be changed completely. Yeah, so you can use different controllers. The two most common ones by default in a navigation to system probably are the dynamic window approach, the DWB controller, and the TEB controller. Yeah, these are the two most common ones that we are going to find in default in typical navigation to systems. Okay? Yeah? And then how it fits the controller in the navigation to stack? Well, basically we have the global planner, and then which is going to create a general plan to go from point A to point B. We are going to have on a lower level the controller, which is going to make sure that the robot properly follows this path while avoiding any dynamic obstacle that might appear. And then finally, we also have the recovery behaviors, which are going to make sure that the robot is able to recover automatically in case that there is any problem. Okay. Then, with the proper introductions being made, let's actually launch a navigation to system, a default navigation to system in the robot, and let's see how this works, okay? Then, here in this project, I have already provided a pre-configured navigation to system so that you just have to start it, okay? You don't have to create it or anything. It is already provided, and all you have to do is to start it, okay? And in order to start it, you have the commands here to follow, yeah? Then, let's do one thing. Let's come here and let's open a second terminal, okay? Important, do not close this first terminal, okay? Because in this terminal is where we have our simulation running. So let's open another terminal so that we can continue executing other commands, okay? Then let's open a second terminal here. Well, let me have a look at the chat here in case that there are any new questions. No. Okay. Is everybody following so far? Are we good to continue? Any questions so far? Yes. All right, then let's continue. Okay. Then, okay, here we have our terminal, and then what we are going to do, first of all, is to start our localization server. Okay? This is another part of a navigation to system. And the localization server basically is in charge of making sure that the robot is able to know always where it is with respect to the environment, okay? So let's start the localization server. You can copy the command again from the notebook and execute it here. There we go. Localization server started. Then we need another terminal, okay? If you want, I would suggest you to, if you double click here in the tab, you can rename the different terminals so that you can organize everything better. For instance, in the first one, I have the simulation. Here, let me rename it. Here I have the localization. Here I'm going to launch RVs, okay? In the third one. So let me go back to the notebook, copy this other command and execute it here in the terminal. Okay. Then, once you execute RVs, you are going to see a pop-up appear here, yeah? With an RVs window automatically appearing here, yeah? Can everybody see the RVs window appearing here after executing the RVs command? Yes? Yes. No questions, good. Yes, okay. Then, yes, okay. Then once we have RVs loaded, we need to provide the initial robot position, okay? Yeah, so how to provide the initial robot position? By using the 2D pose estimate tool here, yeah? Here, you can see a button which says 2D pose estimate, okay? And then you have to provide the pose estimate of the robot with respect to the map. In this case, if you have a top view of the map and you compare it with the simulation, you are going to see that the robot is basically here, where you have this white mark, okay? Then all you have to do is to click on the 2D pose estimate and then drag here on the point, on the white point, and then also point to the correct orientation, which is this one, yeah? Then, once you have the proper initial pose and orientation, you just leave, and then you are going to see a bunch of red points appear, which are for the localization. Also, the laser is going to appear, and also the robot image is going to appear properly here, okay? Yeah? Has everybody localized his robot properly? Yes? Everybody has localized his robot? I'm going to wait for you. Marius has localized his robot. Also Manoj. Also Gilbert. Also Tomás. Okay, excellent. Then, final step. Once we have the robot localized, we are going to open another terminal, okay? This is the fourth terminal. And here we are going to execute the last command, which is this one here. Yeah? Here we are going to launch the path planning systems. Yeah? ROS to launch path planner server pathplanner.launch.py. Then, after executing this command, if you go back to RVs, you are going to see some things also appear now here in RVs. There you go. Here we can see some additional things that are appearing. These are the cost maps, but don't worry, you don't need to know all the details right now. And at this point, we are ready to navigate our robot. Okay? Then, how can we test if the navigation is working? Well, for that, we can use the 2D goal pose. Yeah? Here at the side of the 2D pose estimate, we have another button in RVs, which is named, let me make this a little bit bigger, it's named 2D goal pose. Yeah? Then, if you click on this button and you point it somewhere in the map, basically you are going to be setting a goal for the robot. For instance, I'm going to send my robot here, here in the front, and with this orientation. Yeah? Then, once you send the goal, you are going to see the robot start moving. You are going to see also the path here. And in the simulation, you are going to see how the robot starts also moving. Yeah? Here you can see the robot moving in the simulation, and here we can see the robot following the path in RVs. Yeah? And there you go. Eventually, the robot is going to reach the goal, and you are going to be able to see a message here which says, goal succeeded. Yeah? So this means that our navigation system is working properly. Okay? Yeah? Is everybody able to send goals to the robot? The LiDAR points on the back don't align properly. If this happens, it means that your robot is not properly localized, Alan. Martin says, yes, reach it. I was also able to crash the robot, okay? Yes, yes. And you can send more goals, okay? For instance, I'm going to send now another goal back or here. Let me send another goal here. Yeah. And this green path that you can see here in RBs is the global planner for instance, just so that you know. This green path that appears in RVs is the global planner, okay? Here the robot is doing some recovery behavior, for instance, trying to reach the proper orientation. And there you go, it reached the goal, okay? Yeah? So, here we have the navigation to system working, okay? Now, let me very quickly stop the navigation system and relaunch it, okay? I'm going to stop it, the navigation system. Let me rename this tab to Nav. Yeah, let me put it Nav, okay? And then, if you relaunch here the navigation system, okay, and you check here between the logs, okay, I'm going to scroll up here and look for the logs of the controller server, okay? For instance, I scroll up a little bit, controller server, okay? Here, I can see some things that are being loaded off the controller server, and one of the things I can see, for instance, I have it right here, yeah? I can see here, controller server, created controller, follow path of the type DWB Core DWB local planner, okay? As you can see, here I am using one of the default controllers in Nav2, which is the DWB controller, okay? This is the one that I am using here, okay? I can know this by checking the logs, but also by checking the configuration files, okay? So at this point, what I'm going to do is to open the code editor so that I can properly check all the different packages, files, and everything which is inside this project, okay? Then in order to open the code editor, you have to click on the second button here in the bottom section of the project, yeah? Besides the terminal button, here you have another which says code editor. And if you click here, this is going to open the code editor, and this is going to give you graphical access to all the folders, files, and everything in this project, okay? In this case, we have everything inside the ROS2 workspace, yeah? And inside the SRC folder, here you are going to see everything that we have in this project, yeah? You can see the packages for the simulation, here the localization server, and the path planner server here, yeah? Here is where we have all the files that I am launching for the path planner, which is the systems that I am launching here in the 4th terminal, yeah? And here I have all the configurations for the global planner, for the controller, as you can see, for the recovery servers, for the behavior, behavior trees. All the configuration files, I have them here. Also, you can have a look at the launch files that we are executing. For instance, the one that we are running here is this launch file, right? pathplanner.launch.py. You can have a look at this launch file also from the code editor here. Yeah. These are the contents of the launch file, in case that you are interested or investigating a little bit. And the most interesting part here is the controller.yalm. Yeah? This is the configuration file where we are configuring our Nav2 controller. Okay? And where is the controller specified? It is specified in this parameter, controller plugin. Okay? In this parameter, controller plugin is where we specify which Nav2 controller we are going to be using. Yeah? As you can see here, we are pointing to this follow path, yeah, which is configured down here, follow path. Yeah? And inside the follow path configuration, you can see that we are loading one plugin, which is the DWB local planner. Yeah? And we are also setting a bunch of parameters here related to this controller, which is the DWB. Yeah? So in my navigation system right now, I am using the DWB local planner. Okay? Then in case I would like to change the controller, what I would need to do is to change the plugin that I am loading. Yeah? Let me go back here to the chat. I was able... You are using behavior tree to monitor the robot's movement? Well, behavior trees are used by default in navigation too. Okay, here you have the behaviors configuration. Okay, but yes, so behaviors are used by default in navigation too, in any navigation to system. Okay. The points are better as it moves. Seems it is updating. Yes, that is the expected behavior, Alan. The more you move the robot, the better it should localize itself. The recovery movements are set by default. Is useful to modify them? Yes. So by default, you have some recovery behaviors, and depending on your robot, it can be helpful for sure to update them. Yes, Franco. Okay. Then let's continue. So what if we want to change the controller to use? Well, here is where we are going to introduce the vector pursuit controller. Okay? The vector pursuit controller is a specific type of path following controller used in mobile robotics. And it is designed to follow a pre-planned path. Yeah, this path is provided by the global planner by generating velocity commands that drive the robot along the path while maintaining a smooth and efficient motion. Okay? This is basically the definition of a controller, of any controller, right? It is designed to follow a pre-planned path by generating velocity commands that drive the robot along the path while maintaining a smooth and efficient motion. This is basically the purpose of any controller. Then what's special about this controller? Well, there are many things, but for instance, this controller has a very low computational overhead and is very easy and simple to deploy. Yeah? Here you have some more information. It tracks path orientation in a geometrically meaningful way, making it an ideal replacement for the pure pursuit algorithm in scenarios where path following accuracy is vital. Okay? I'm not going to get into lots of details about this specific controller because we don't have basically time, but here you have a link in case that you want to check to the official repository. Okay, this is the official repository of the people, which are the people at Black Coffee Robotics. They have developed this Nav2 controller, and here you have all the explanations of how to install it. Yeah, so you have to download the repo and compile it. In our case, as you can see here, in the ROS2 workspace, you already have it. Yeah, I have already downloaded this code and compile it inside this project, so you don't have to do it. But here you are going to find instructions of how to install it, and you have also links to even papers, yes, of script theory. You can have, here you have all the information that in case that you want to go into deeper details. Also down here you have some more theoretical explanation of the vector pursuit algorithm, okay? And also all the details about the parameters. Yeah. Here also in the notebook I have included some information about the relevant parameters down here. But basically, what are the main features that this controller provides? Here you have them. So, adaptive look-ahead distance. Yeah. The look-ahead distance is used to find the target pose on the path. Yeah. This is a bit theoretical, so I'm not going to get into much more details here. But also, another interesting feature is that it provides collision-aware linear velocity. Yeah. So the robot's linear velocity is automatically scaled when in proximity to obstacles. Yeah, this is something interesting. So if the controller detects obstacles close to the robot, then the velocity of the robot is going to be scaled. Yeah. Also, approach-aware linear velocity, which means that the robot's linear velocity is automatically scaled when nearing a goal pose, when getting close to the goal pose. Also, on point rotation, which means that the controller will first rotate on point when attempting to chase a target pose at a heading which is more than the robot's current heading. Yeah? And another very interesting feature, which we are going to test in today's class, is the optional reversing, which means that the controller will output reverse velocity if the look-ahead point, if the goalpost is behind the robot. This is something very interesting because let me show you something. So by default, what happens if I send a goal to the robot which is right behind the robot? Yeah. So right now the robot is in this pose and looking in this direction. So what happens if I send a goal which is right behind the robot and with the same orientation? What is going to happen? You're going to see. The robot is going to completely rotate, then it's going to go to the goal pose, and then it's going to rotate again. See? As you can see, this is not very efficient, right? Because it would be much easier if the robot just moves backwards, right? But this is not the behavior. Yeah? Let me show it again. Instead of just moving backwards a little bit, the robot does a complete rotation, then it goes to the goal pose, and then it rotates again, right? Then, for instance, with this controller, we can change this by using the reversing option, okay? Yeah? Then, what is the task for today's class? The task for today's class, you have it down here, is to change the controller used by Nav2. Yeah? So modify the controller configuration to use the vector pushing controller. If you achieve to do so properly, you should be able to see the following output when you launch the controller server. Yeah? This is the expected output. And then, once we have, besides this also, you need to fine-tune the parameters of the controller in order to allow the robot to use reverse velocities in order to achieve a goal which is behind it, right? Then, step 1, modify the controller configuration to use the vector pushing controller. So, I'm going to do this right now. I'm going to solve it, okay? So that you see how to do it. Then, here in the notebook, you have an example configuration of the vector push controller, okay? So what I'm going to do here is to stop the path planning systems, and then what I'm going to do is to copy this configuration from here, okay? I'm going to copy all this configuration in the follow path, and then I'm going to replace, Control Z. Yeah. So I'm going to remove the current configuration that I have inside follow path in my file, and instead I'm going to paste here. Did I copy from the notebook? Let me do it again. Let me select all these, copy, and then paste here. There you go. Okay? Yeah? So now, in my controller YALM, inside the follow path, I am loading the vector pursuit controller. Yeah? And besides loading the vector pursuit controller plugin, also I am setting here all the parameters required by this controller. Yeah? Which you can find explained here in the notebook, but also here in the official documentation. Yeah? Here you have all the parameters and what they are used for. Okay? Yeah? Then I change the old, let me do it again. Yeah? So the default configuration where I am loading the DBW local planner and all its parameters, I'm going to completely remove this, and instead I'm going to paste the code that I have in the notebook, which loads the vector push it controller, okay? Then once I have this, what I'm going to do is to build again, okay? I need to compile my workspace, okay? Because I have modified this file. So in order for the system to take this file into this new file into consideration, this updated file into consideration, I need to recompile, right? So let me recompile here. Remember, very important to compile in the ROS2 workspace folder, okay? Not in any other path, but in the ROS2 workspace. Very important that you compile here, okay? So I am recompiling. Then once I finish compiling, I source the workspace. And then now I can relaunch the path planner systems. Let me do that. And if I have done it properly, I should be able to scroll up here, look for the controller server logs. Let me look for the controller server logs, which are here, controller server. And then here I can see, here I have it. Yeah. Created controller follow path of type vector pursuit controller, vector pursuit controller. So as you can see, now my system is loading the vector pursuit controller. Yeah? Then let's see if I can send goals. Let me send a goal here to the robot. Yes. So the controller is working properly. My robot is able to navigate properly with the vector pursuit controller. As you can see, goal succeeded. And what happens if I send a goal which is behind the robot, as I was doing before? Let me do this. Okay, it's not working yet, right? Because the robot is rotating. It's doing it the long way, right? Rotate, go to the point, and rotate again, okay? So basically, the first part of the task, which is to modify the controller configuration to use the vector pursuit controller, check. This one I have it working. But the second part, which is fine-tune the parameters in order to allow the robot to use reverse velocities, this one I don't have it. So how can I achieve also this second one? I'm going to explain it to you, yeah? So as I was explaining earlier, this feature is the optional reversing feature, right? Which is the controller will output reverse velocity if the look ahead point is behind the robot, yeah? So here in the notebook, I have added the feature parameters. And if we check the optional reversing feature, you can see that this is managed by the allow reversing parameter, yeah? And then if we go inside the configuration of our controller, you can look for this allow reversing parameter, which we have here. And as you can see, we have it set to false, yeah? So if I want this feature to work, I need to change this to true, right? Yeah? So very important. Everybody find the allow reversing parameter and change it to true, okay? And then once I have it to true, I'm going to need to stop my path planning system, recompile again, right? Because I need to take into account this new change in the configuration. So I need to recompile. Once I have recompiled, I source, and then I can relaunch the path planning systems. There we go. Okay. And at this point, let me try again. Let me send a goal which is here in front. There we go. My robot goes properly to the goal, also in the simulation. And then let me put actually the simulation here, side by side, so that we can see this better. And then now I'm going to try again to send a goal which is behind. Actually, I think it's going to be better like this. RV is in the left, simulation in the right. There we go. And then let me send now a goal here behind the robot with the same orientation. Let's send it here, okay? And voila, now the robot just moves backward in order to reach the goal, yeah? So we have a much more optimized path in order to reach a goal which is behind the robot, yeah? Instead of doing all the rotation and everything, the robot just, okay, I'm going to just move backwards. Yeah? Okay, so here we have learned how to integrate a custom Nav2 controller into our navigation 2 system. Okay? Yeah? Has everybody been able to have this demonstration working? Yes, no? Let me have a look at the chat. That is indeed useful, says Alan. Is vector pursuit better than PMMI? I don't know about PMMI, Mihail. I don't know. Why didn't you use, well, because in this case I just did it with Qualcomm build for simplifying things, okay? Gilbert says yes, Martin yes, also Manoj working well. Okay, awesome. Awesome. So yeah, in case that you want to learn more about this specific controller, compare it with others, okay? You have this project which you can use it and you can work with it whenever you want, okay? Right now I have shown you how to integrate a custom controller, but as you can see, there are many parameters, many features that you can customize depending on your needs. So you can do your own testing, okay? It's different to pure pursuit algorithm, Martin. How to launch it? Repeat, please. How to launch what? What do you mean? How to launch it? You have the instructions here in the notebook, okay? How to launch it is here with the path planner.launch, okay? What you need to do is to make sure that you properly update the controller.yalm with the follow path information, yeah? Actually, this is not anymore this is now the vector, how it was, vector pursuit controller, yeah, vector pursuit controller parameters, okay? So Martin, answering your question, I'm not a super expert on this specific algorithm and everything, but for what I have understood of reading a little bit the documentation, it is like an optimized version of the pure pursuit, okay? All right, then once we have this working, I want to try out something, okay? Let me try to connect to a real LIMO robot, okay? So I'm going to stop everything at this point. And I want to actually try all this, but with a real LIMO robot. Okay, this part, you are not going to be able to do it. Okay, so for this part, you can see and check how I do it. Okay, so let me connect here to the real robot by connecting to the lab. Let me go there, turn on the lab. Okay, I'm getting connected to the lab. There we go. Here I should see the cameras now loading. There we go. So this is a real camera live right now. This is a room that we have here in our offices, okay? And this is, as you can see, a very basic environment, and we have here a real LIMO Pro robot, yeah? So far we have been working with the simulated version of the robot, but here I am with a real LIMO robot, okay? And now I want to basically try out all this with the real robot, okay? Let's see if I can also use this custom controller, this vector pursuit controller with the real robot. So first of all, let me make sure that I can see the topics of the real robot, that I am properly connected. Okay, it seems I am. And then I'm going to repeat the steps to launch the navigation system, okay? Here, if you pay attention to the files in the code editor, you are going to see that I have duplicates of all the configuration files which have the real suffix, yeah? Also, I have a launch file for the path planner for the real robot, and also I have another launch file for the real robot for the localization, yeah? So these are the ones that I'm going to use for the real robot. Then let me copy all the steps here. First of all, launch the localization, but instead of localization, I'm going to launch the localization underscore real. There we go. Let me launch RVs in a second terminal. Here, RVs, and I am going to open a third terminal. Okay, then let me see. In this case, I need to see where the robot is. It's more or less in the middle of the room and looking at this direction. So I would say that more or less, let me set the localization, is something like this, more or less. Okay, I would say. Yeah, let me get a bit closer here. Okay. Wait, there was an error here. Am I seeing the... Let me check something. I think I don't have the laser for some reason. Oh, probably I need to just update this to best effort, right? There we go. Okay. So it is not perfect. Then I'm going to do something here in order to improve the localization, which is to move manually the robot a little bit. Teleop twist keyboard, teleop twist keyboard. Okay, let me then, here I'm going to move manually a little bit the robot in order to get a better localization, because as you can see, the laser is not matching very well the map, okay? This means that the localization is not very good. So I set an initial pose which is not very accurate. So let me fix this by trying to move a little bit the real robot manually with the keyboard. Let me do this. The camera paused for some reason. Let me click play again. There you go. Okay, so there you can see that I am moving the real robot. Let me rotate a little bit like this. And then localization should get... not yet. Let me move a little bit more. The robot around. Let me move it maybe here. Rotate a little bit. Yeah. So the more I move the robot, the better the localization should keep getting. Okay. Let me see. Yeah. So as you can see, now it's basically perfect. Okay. Then at this point, I'm going to stop, and finally, I need to launch the path planner. Right here. Important to update, to change to the real launch file. There we go. So now I should see here in RVs the cost maps, and then I should be able to send goals. So let me put RVs. Actually, let me put this here and the real robot here. There we go, and RVs, I'm going to put it here like this. Okay, let me try to send a goal then, which is more or less here in the center. Okay, so we can see there the robot is following properly the goal, and now what I want to basically test is the new controller, right? So let me, well, first of all, let me check in, I can check in the terminal here to make sure that the proper controller has been loaded, and I can see here that yes, I am loading the vector pursuit controller, right? And then now I want to try to send a goal here in the front, and then I want to send a goal which is behind and see what happens, right? So let me try to send a goal which is right behind the robot. well, let me add something so that I can know where the robot is. Let me add some, for instance, TFs here. Okay, so my robot is here. And then let me send here a goal pose, which is right behind the robot here, with the same orientation. And then you can see that the robot is moving backwards in order to reach the goal, which means that actually I am using the custom controller and I can tune this feature of allowing the robot to move in reverse velocities. Yeah? Okay, so you can see this is a very interesting demonstration to show that whatever you practice in the simulated environment, you can also practice it with the real robot. And this is an awesome way of teaching robotics or of learning or of practicing robotics. Yeah? First, you test things in a simulated environment, and once you have things working more or less, you move to the real environment. Yeah? If I want to configure motors for my robot, is it Nav2 controller that I need? Well, Rafael, I don't know what you mean by configure motors. If you mean to configure the no. The Navigation 2 controller assumes that your motors are already working properly. Yeah. So if you want to configure directly the motors, then what you have to change are the drivers, basically, of the motors, yeah? But then the navigation controller assumes that your robots are properly configured. What is the gray, Sham is asking, what is the gray colored boundary around the wall? Is it a restricted region for robot movements? That's a good question, interesting question. This gray thing are the cost maps, okay? These are known as the cost maps. This is a navigation 2 concept, okay? But basically, it's these black areas, which are the obstacles, with some inflation applied to them. Okay, but this is known as cost maps in Nav2. Okay, it's a very common navigation concept. All right. So yeah, then I'm going to leave it here with this final demo with the real robot. Let me just remind you very quickly that we have this super cool promo right now, in case that you also want to get one of these real robot guys. We have this promo of the LIMO Pro with the coupon code, which it's going to be available until September 3. Very interesting, super cool robot. We have some of them here in our facilities, and they are really cool, really awesome robot. And yeah, with this, I'm going to leave it here. I hope. Let me check some last questions here. Is there any Nav2 tools scripts to do the part you did? Wondering manually? Is there any Nav2 tools to do the part you did manually? Wondering. I don't know what do you mean by wondering. Manoj, I don't understand this word. Wondering. Thanks, Alberto. Last question. Have you preloaded map in the robot there for that specific scenario? Yes. Franco. Yes. So I am using, here in the localization launch files, you can see that I am launching a map server instance, and here I am loading a map. Okay? So I am loading a map of the environment. Yes. Here is where I am loading the map. Can we also run real robot? No, unfortunately, because you cannot run it here. In this case, okay, we have some labs available, but this one is something that we have created for this class only, so you cannot use it. But you can always get a real LIMO robot using our promotion. Okay? Yeah, I already have the map. Yes. All right, guys, then I'm going to leave it here. Thanks a lot for being here with me in this class. I hope that you enjoyed it. I hope that you have learned something new. As always, you can do your own testing and share your work with us in our social media. And yeah, I will see you in the next one, next Tuesday. And as always, until then, keep pushing your robotics learning. Bye-bye.